Imagine a six-piece ensemble hired to play in 3 rooms. In the first room, 5 instruments are loud, correlated, and easy to measure. In the second, the acoustics change, but the same 5 still carry most of the song. The sixth musician barely registers in the average recording. A compression algorithm walks in with a clipboard, sees almost no average energy, and removes that musician. Excellent. The spreadsheet is now lighter. The deployment graph has a satisfyingly smaller rectangle. Somewhere, a product manager senses a future slide deck. At this point, tung sahur is God, not scientifically or theologically, but in the strictly operational sense that the quiet drum is carrying the only basis vector preventing a rare room customer support incident. Then the ensemble enters the third room. This room is rare. Maybe only 0.2% of ordinary traffic resembles it. But in this room, the 5 common instruments cancel, and the quiet sixth instrument is the only one carrying the melody. The compressed ensemble fails completely. The average metric still looks healthy because average metrics are very calm people. They can watch a tiny population fall through a trapdoor and report that the carpet remains mostly level. This episode is about a research paper that turns that failure into a precise question. The paper is called Distribution Robust Functional Subset Projection for Structured Neural Network Width Compression. The title sounds like 7 committees merge their calendar. The central idea is much cleaner. When we remove complete hidden units, we should judge candidates by the functions they contribute across environments, and we should explicitly protect the environment with the worst reconstruction. The word environment does not have to mean a physical place. It can mean prose, dialogue, or code. It can mean a demographic subgroup, a sensor regime, a language, a lighting condition, or a rare operational state. The important point is that each environment induces a different activation pattern. A hidden unit that looks redundant under one distribution may provide a unique activation direction under another. This matters because compression is normally calibrated on a finite sample. If the sample mirrors prevalence, common behavior supplies most gradients, most matrix energy, and most opportunities to look important. Rare behavior may be well represented enough to evaluate, yet too lightly weighted to influence selection. The method does not require us to pretend rarity is unknowable. It asks us to name environments before compressing and inspect their reconstruction separately. That turns a vague concern about hidden regressions into a matrix whose rows, risks, and failures can be audited. We will build the method from the operator level. A unit is not merely a scalar weight or a neuron with an impressive magnitude. Its functional contribution is the product of where it activates and what direction it writes. We will define normalized reconstruction risk, separate subset selection, from weight refitting, derive the closed form refit, and see how a minimax objective moves attention toward the environment currently suffering most. Then we will make the method more ambitious. The paper constructs compact functional fingerprints, clusters units hierarchically, and asks where a dendrogram should be cut. It distinguishes 3 meanings of width that are very easy to blur together. Finally, we will look at the evidence. In the controlled rare environment construction, robust selection wins perfectly. 120 stable choices out of 120. In a controlled 100 to 50 compression problem, right-aware hierarchy recovers all 50 dominant families. And then GPT-2 arrives and ruins the victory montage on a limited diagnostic across 3 layers and 3 text environments. The elaborate Gaussian hierarchy does not earn the win. A simpler, robust capacity selector is better on average at aggressive reduction. That negative result is not a failure of the episode. It is the episode. It separates the robust principle from one ornate implementation. Keep one question visible throughout. What behavior disappears when the width becomes smaller? Parameter count tells us how much was removed. Functional reconstruction tells us what the deletion actually did. Before touching the method, separate 5 operations that are frequently thrown into one bucket labeled compression. Quantization changes numerical precision. The topology may remain identical, but a weight that once occupied 16 bits might occupy 8, 4, or fewer. Unstructured pruning sets individual weights to 0. This can create impressive sparsity while leaving hardware with the awkward task of discovering that most of a dense matrix is now decorative absence. Structured width compression removes complete channels, neurons, attention heads, or intermediate dimensions. The matrices themselves become smaller. If an MLP originally expands a residual stream from dimension D to width M with compression, chooses a smaller k and constructs an operator with shape d by k by d instead. This is attractive because ordinary dense kernels can execute the new shapes, but the structural convenience creates a harder scientific obligation. Deleting a complete unit deletes its activation behavior everywhere. Low-rank approximation changes the factorization of an operator. Instead of choosing original units, it may learn new basis directions. Depth compression removes blocks or layers, changing the number of sequential transformation. Distillation trains a smaller model to imitate a larger one. These techniques can interact, but they do not make the same intervention. Saying that one compression result proves another is like testing a diet by weighing the refrigerator. The paper isolates structured width reduction. It does not claim a complete production compressor. It does not demonstrate wall clock acceleration, lower energy consumption, or universal downstream robustness. The GPT-2 intervention is local. One MLP is compressed at a time. At the reported reduction levels, that removes only about 0.95, 1.90, and 2.28% of total GPT-2 small parameters. Those are diagnostic interventions, not a press release announcing that GPT-2 now runs inside a calculator. Shape reduction can enable speed only after the rest of the stack cooperates. The retained width must align with kernel-friendly dimension. Index gathering must be compiled away rather than performed on every token. New dense matrices must replace masked old matrices. Memory traffic, batching, quantization, and downstream layers can dominate the final latency. A paper can establish that an operator is reconstructible at width k without establishing that a particular runtime executes it faster. The distinction is not pedantry, it is the distance between a mathematical compression ratio and an invoice from the inference cluster. Why study such a controlled slice? Because mechanism studies let us ask a clean question before systems effects pile on. Suppose an MLP has M candidate hidden units. We want k of them with k smaller than m. We are not allowed to invent arbitrary new activation functions. We select a subset of existing activation columns and then refit their outgoing writes. This produces a constrained projection problem. That word constrained matters. If we used an unconstrained low-rank factorization, a new basis could rotate toward whatever directions. Minimize average error. Subset selection is harsher. The activation bases must come from actual surviving units. This makes the intervention interpretable and deployable, but it means one omitted activation family may be impossible to reconstruct after the fact. The episode therefore uses 3 ledgers. The shape ledger records how many units survive. The parameter ledger records how much of the whole model changed. The functional ledger records reconstruction risk in each environment. A method does not get to move a number from one ledger to another because the thumbnail would look better. We also need a baseline. If a compressed operator predicted 0 everywhere, its normalized risk will be approximately 1 under the paper's energy. Normalization values far below 1 mean the retained subset reconstructs much of the original operator. This normalization lets environments with different raw output energies appear on a comparable scale. Without it, the loudest environment can dominate simply because its vectors have larger norms. So the problem is not merely which weights are small. It is which original activation directions can be removed while the surviving units after a legal refit preserve function across every environment we care about. Now build the functional object. Choose an environment E. Run n sub E calibration examples, tokens, or positions through the original network. For candidate unit I, collect its scalar activation at every sampled position into a column vector a sub E comma I. This vector answers where and how strongly the unit fires in that environment. Next, take v sub I, the outgoing write vector for that unit. In an MLP, the activation is a scalar coefficient, and the write vector specifies the direction added back into the output space. Multiply the activation column by the transpose of the write vector. The result is an outer product. F sub E comma I equals a sub E comma I times v sub I transpose. This matrix is the unit's functional contribution over the sampled environment. Each row corresponds to a calibration position. Each column corresponds to an output feature. A bright row means the unit activates strongly there. The pattern across columns shows what it writes. Activation without write has no effect. Write without activation remains an unemployed vector waiting beside the residual stream. Stack all M activation columns into a sub E. Stack all outgoing write vectors into V. The complete operator output is Y sub E equals A sub EV. This is just the sum of every unit contribution, but matrix notation lets us state the compression problem cleanly. Select a subset S containing K unit indices. A sub E comma S keeps only those activation columns. After selection, we fit a new write matrix B. The compressed output becomes a sub E comma SB. Notice what is allowed to change and what is fixed. Selection fixes the surviving activation basis. Refitting may change how those surviving columns write into output space. It may rotate and rescale their outgoing effects. It may not create an activation column that was deleted. This is why weight magnitude can be misleading. A unit with a modest write norm may activate in a unique environment on unique positions. Another unit with a huge write norm may track a family of near duplicates. Looking only at V ignores where the unit fires. Looking only at A ignores what it writes. The outer product puts both halves into the same object. There is also a rescaling symmetry. Multiply an activation column by C and divide its write vector by C. The functional outer product remains unchanged. Raw activation magnitude or raw write magnitude alone changes under this parameterization, even though the function does not. A functional criterion should be far less impressed by cosmetic rescaling. Neural networks contain enough arbitrary scale conventions already. We do not need the compression metric developing a crush on one of them. The visual geometry is useful. Imagine every activation column as a rail running through calibration positions. Every write vector is an arrow in output space. Their outer product is a sheet swept out by the rail and arrow together. The full operator is a stack of these sheets. Width compression removes entire sheets but is allowed to repaint the arrows attached to sheets that remain. If two candidates activate in nearly the same pattern and write in nearly the same output direction, their sheets are redundant. Keeping one representative may be safe. If two candidates have similar activations but opposing writes, merging them blindly can fail. If their writes are similar but they activate on disjoint environments, one may be essential. Functional similarity has to see both sides. This formulation also provides the bridge to transformers. For an MLP block, calibration positions may be tokens drawn from prose, dialogue, and code. The output Y sub E is the original MLP contribution at those tokens. Local reconstruction asks whether the compressed MLP reproduces that contribution before we measure how the altered residual stream affects perplexity. To make the shapes concrete, suppose an environment contains 320 token positions. An MLP has 100 candidate units, and the residual width is 768. Then a sub E is 320 by 100. V is 100 by 768. Their product Y sub E is 320 by 768. If we retain 50 units, A sub E comma S becomes 320 by 50, and B becomes 50 by 768. Every dimension on screen has a job. None is a decorative subscript wearing glasses. We now have the thing being preserved. Next, we need a risk that does not let a high-energy or high-prevalence environment purchase every vote in the election. For each environment, the target is the original output Y sub E. The compressed reconstruction is A sub E comma SB. Their difference is a residual matrix. Square its Frobenius norm, and we have total reconstruction error across positions and output dimensions. Raw error is not enough. An environment with larger outputs naturally produces larger residuals. The paper defines D sub E as 1 over N sub E times the squared Frobenius norm of Y sub E, plus a small epsilon. This is the original output energy, per sample. Then environment risk R sub E is the squared reconstruction error, divided by N sub E D sub E. The normalization creates an interpretable reference. Predicting 0 gives risk close to 1. Perfect reconstruction gives 0. A risk of 0.02 means the residual energy is roughly 2% of the environment's target energy. Under this it does not mean accuracy is 98%, and it does not promise the downstream task changes by exactly 2%. Reconstruction risk is a local functional metric, not an all-purpose happiness score. Now choose how environments vote. A source-only objective minimizes R1. This is appropriate if only one calibration distribution matters, but it provides no protection elsewhere. A prevalence-weighted mean minimizes the sum of pi sub E times R sub E. Pi may reflect how often environments appear. This improves overall reconstruction under that mixture. But a rare environment receives a tiny coefficient. The distribution robust objective minimizes the maximum R sub E. Every environment can become decisive if it is currently reconstructed worst. The method does not pretend that all possible future distributions are known. Robustness is only with respect to the supplied environment set and the chosen local risk. If code is absent from calibration, the objective cannot protect a code behavior it never observed. The minimax sign is not a small wizard who discovers missing populations. Consider prevalences 0.499, 0.499, and 0.002. Each environment may still contain the same number of calibration samples for evaluation, but the mean objective gives the failure environment 1/250th of the combined weight of the common environment. A candidate that is excellent in the common pair and disastrous in the rare environment can still win the average. On screen, 3 risk bars move. Under source-only selection, the first bar shrinks and the others may do whatever unobserved systems do when nobody is looking. Under the prevalence mean, 2 common bars dominate the weighted total. Under minimax, the tallest bar defines the current objective. The optimization pressure moves toward whichever environment is suffering most. A tiny numerical example makes the policy visible. Imagine common environment risks of 0.01 and 0.02, and rare environment risk, 0.8. With prevalences 0.499, 0.499, and 0.002, the weighted mean is only a little above 0.015. The maximum is 0.8. Both numbers are correctly computed. They answer different questions. The mean describes expected reconstruction under the chosen mixture. The maximum describes the largest relative failure among named environments. Robustness begins by refusing to let those two sentences impersonate each other. The mixture average has slept through sahur, woken at noon, and confidently reported that the alarm performed well on average. The paper also defines a gap. Maximum risk minus weighted mean risk. A large gap warns that the average is hiding uneven reconstruction, but the gap is diagnostic. Minimizing it alone could produce uniformly mediocre behavior. The actual robust objective targets the maximum risk. Why normalize each environment independently instead of pooling all rows? Pooling lets sample count and raw output energy determine importance before the objective even begins. Environment normalization states the policy more openly. Reconstruction damage is measured relative to what that environment originally produced. This is not automatically the morally correct policy for every application. Some failures may deserve weights based on severity, legal obligations, uncertainty, or population risk. The paper studies source, prevalence, mean, and worst environment objectives in a controlled framework. Production systems still have to decide which environments exist and whether equal worst-case protection matches the real cost of failure. But as a scientific instrument, max risk exposes something the mean can conceal. The average can answer how much reconstruction error exists under this mixture. The maximum asks, who is paying the largest relative cost for the compression? Once a subset S is fixed, refitting B is a convex weighted ridge problem. Define L sub Q of B given S as the sum over environments of Q sub E times R sub E, plus lambda times the squared distance. From an initial right matrix B0, the Q weights specify which environments matter during this refit. Lambda stabilizes the solution and optionally keeps it near the inherited rights. Substitute the normalized risks. Each environment receives alpha sub E equal to Q sub E divided by N sub E D sub E. Different sample counts and output energies are now explicit in the coefficient. Differentiate the objective with respect to B, set the gradient to 0, and collect terms. The derivative is ordinary matrix calculus. The residual term contributes 2A transpose AB minus 2A transpose Y, scaled by alpha. The ridge term contributes 2 lambda times B minus B0. Set their sum to 0, move target terms to the right, and the factors of 2 disappear. The result is not a neural network mystery. It is regularized least squares repeated across environments with carefully chosen normalization. That simplicity is useful because the refit can be solved and tested independently from the subset search heuristic. On the left appears the weighted sum of A sub E comma S transpose A sub E comma S plus lambda I. This is the regularized Graham matrix of the surviving activation basis. Multiply it by B star. On the right appears the weighted sum of A transpose Y plus lambda B0. Solve this linear system and we have the exact optimum for B under fixed S and Q. The important phrase is under fixed S. The solve is exact for the refit subproblem. The full subset problem remains combinatorial. Choosing K of M candidates creates M, choose, K possibilities. The paper uses greedy or hierarchy-based selection depending on the experiment and compares the tiny, rare environment construction with exhaustive enumeration. For a minimax refit, Q is not held fixed forever. Begin with environment weights, solve exactly for B, evaluate each R sub E, then increase weight on environments with larger risk using exponentiated gradient ascent. Normalize Q and repeat B, minimizes weighted risk for the current Q. Q moves toward the environment that can make the result look worst. This alternating procedure is an approximation to the saddle problem. The paper does not claim a formal saddle certificate for the finite iteration schedule. That caveat belongs on screen because algorithm diagrams have a dangerous habit of turning arrows into theorems. Now the key limitation. Suppose a rare environment requires an activation column, that's selection removed. Refitting can change B, which changes how surviving activations map into output space. It cannot add the missing column back into a sub E comma S. If the target contains a component outside the span of surviving activations, residual error remains. Visualize a shelf of basis rails. 3 rails survive, a 4th used only in the rare room has been removed. The refit can rotate arrows attached to the 3 surviving rails. It can make combinations of those rails. It cannot generate motion along the missing 4th rail. You may repaint the surviving doors. Atom can optimize the surviving choir until human resources opens a case. It still cannot respawn tongue's missing drum. Resurrection is not in the matrix API. This distinction explains an important controlled result. Robust refitting can reduce damage after a fragile subset is selected by increasing weight on the failure environment. It finds the best possible rights on the surviving basis. But it cannot match robust selection when the stable candidate contributes a unique activation direction. The selection decision determines whether the representational ingredient exists at all. There are therefore 2 separate robustness questions. Robust selection asks which units survive. Robust refitting asks how surviving units are recombined. A production compressor could use both, but evidence for one is not evidence for the other. The normal equation also reveals numerical concerns. If surviving activation columns are highly collinear, the Graham matrix is ill-conditioned. Lambda improves stability. Solvers should avoid explicitly inverting the matrix. They solve the regularized linear system. Code should preserve floating point precision during the fit even if deployed weights are later quantized. At this point, the basic robust mechanism is complete. We can score a candidate subset with normalized environment risks, refit its outgoing rights exactly for fixed weights, and move Q toward the worst environment. The next problem is combinatorial scale. How do we find representative units without testing every subset? Exhaustive subset search becomes impossible quickly. Even 100 choose 50 is roughly 1 times 10 to the 29. The Sun will submit a bug report before that loop finishes. The paper therefore builds a compact representation of each unit's function and uses hierarchical clustering to identify families. Begin on the right side. The outgoing vectors live in a d-dimensional output space, but their meaningful variation may concentrate in a lower dimensional subspace. Compute an output basis P, typically from leading singular directions. Project V sub I through P transpose. This gives a lower dimensional description of where the unit writes. Now compress the activation side. For each environment, draw a Gaussian probe matrix G sub E with P rows and N sub E columns. Multiply G sub E by a sub E comma I. Instead of storing the full activation trace, we keep P random linear measurements. Combine the projected activation with the projected write through another outer product, vectorize it, and divide by the square root of D sub E. The result is Z sub E comma I, a compact functional fingerprint. The construction is not arbitrary decoration. Take two candidates, I and J, in expectation over the Gaussian probe. Their fingerprint inner product equals an activation inner product, normalized by environment energy multiplied by the inner product of their projected writes. Similar activation and similar write produce high similarity. Disagreement on either side reduces it. The expectation follows from the Gaussian identity that G transpose G behaves like an identity map in expectation, up to the probe normalization convention. The random projection therefore preserves activation inner products on average, while P restricts writes to the chosen output subspace. A finite probe is noisy. Increasing P reduces sketch variance, but costs memory and compute. Increasing output rank R preserves more write detail, but enlarges every fingerprint. The method exposes a compression problem inside the compression problem. How much functional geometry must be retained to choose which units survive? Concatenate or aggregate fingerprints across environments. Then compute cosine distance, 1 minus normalized cosine similarity. Build an average linkage hierarchy at a requested width K. Cut the tree into K clusters and select a midoid from each cluster. A midoid is an actual candidate nearest the cluster under the chosen distance, not a synthetic average unit. After selection, perform one global refit across environments. The tree is useful because it stores many candidate widths in one nested structure. A cut near the leaves retains fine distinctions, a higher cut treats larger families as redundant, but a dendrogram does not know the correct deployment budget. It organizes similarity. A separate stopping policy chooses K. The paper compares a raw right-aware hierarchy with the Gaussian fingerprint hierarchy. It also introduces an optional coordinate-wise bootstrap Gaussian regularizer. Bootstrap samples estimate a mean and variance for fingerprint coordinates, then adjust similarity according to uncertainty. The manuscript is careful. This is a working coordinate-wise regularizer, not a calibrated Bayesian posterior. Calling every variance estimate a posterior is how method sections become fantasy novels. Computational cost matters. Constructing fingerprints scales roughly with the probe count, calibration positions, candidates, output dimension, and retained output rank. Pairwise distances and ordinary hierarchical clustering require order m² work and memory in the number of candidate units. That may be manageable for a single MLP width, but becomes a bottleneck at much larger scales. The paper does not hide the quadratic table behind the phrase efficient geometry. What does the hierarchy preserve? In the controlled family experiment, candidates include positive rescaling clones, nuisance near clones, zero right distractors, and low energy auxiliaries. A good hierarchy should group functionally equivalent variants, while keeping one representative from every dominant family. An energy floor filters tiny contributions that can otherwise influence similarity or stopping. The visual scene uses 4 linked panels. First, an operator sheet. Second, the output basis P retaining major right directions. Third, Gaussian probes compressing activation traces into small bars. Fourth, a fingerprint tile entering a dendrogram. Hover is not allowed because this is a video, a fact several dashboard designers learn only after shipping the tooltip. At the tree cut, one representative node lights in each cluster, the others dim, but remain visible long enough to communicate what was removed. A global refit arrow then points back to the operator reconstruction. Selection and refit remain separate even in the advanced method. The hierarchy is an engineering hypothesis. Functional geometry should reveal redundant families better than simple scalar scores. Controlled experiments support part of that hypothesis. The GPT-2 diagnostic will show where the evidence stops cooperating. The paper's stopping discussion is easy to misread unless we separate 3 quantities. First is measured non-zero width or rank. How many directions are detectable under a particular numerical threshold and representation? In the controlled 100-unit construction, 70 non-zero measured directions remain after obvious zero right candidates are excluded. Second is dominant family width. The construction intentionally contains 50 underlying functional families. Clones and nuisance variants increase measured diversity without increasing the number of families the experiment considers essential. Recovering 50 families is therefore different from reporting rank 70. Third is operating width. This is the case selected by compression policy after balancing reconstruction risk, cost, and perhaps downstream constraints. It is not a metaphysical property hidden inside the network. Change the energy floor, probe dimension, calibration distribution, risk tolerance, or deployment budget, and the chosen operating width may change. The paper examines spectral gaps and hierarchy gaps as candidate stopping signals. Raw fingerprints without an energy floor can see approximately 70 directions, adding a 5% energy floor moves estimates toward roughly 65. Gaussian sketches without the floor trend around 55. and Gaussian plus the floor approaches 50 in the controlled setup. These numbers do not prove that every network has a true intrinsic width discoverable by one gap. They demonstrate a rate distortion policy on a construction with known families. The method asks how much functional distortion we accept for a smaller retained set. The answer depends on what counts as signal. Our visual uses three concentric measuring devices. The outer spectrum counts detectable non-zero directions. A middle ring groups dominant families and adjustable inner aperture marks operating width. The rings never merge into one label. If a slide says intrinsic dimension while pointing at all three, an alarm icon appears and quietly revokes the slide's tenure. This distinction also clarifies why an energy filter can help. Very low energy units may create extra directions or small branches in a hierarchy if their contribution is beneath the chosen distortion budget. Filtering them can reveal dominant structure, but the filter can also erase rare, low-energy behavior. Its threshold is therefore a policy decision that must be tested across environments, not a free denoising spell. The robust objective and stopping policy interact. Worst environment risk may require retaining a family that is globally low energy, but locally essential. A global energy floor could remove it before robust selection gets a vote. Implementation should calculate energy with environment awareness, or at minimum audit which environments lose candidates at the filter stage. An operating policy should therefore produce a curve, not merely one sacred width. For several values of K, record mean risk, worst risk, family coverage, where known downstream quality, parameter reduction, and measured runtime. Mark the knee only after uncertainty and deployment constraints are visible. If two adjacent widths have indistinguishable quality but one aligns with a faster kernel, the system's result may choose it. If the smaller width creates a sharp rare environment jump, the curve has identified the price of that final deletion. Measured width describes the representation we observed. Family width describes the controlled generative story, or an inferred clustering. Operating width describes the compression decision. Keeping those nouns separate prevents a useful heuristic from being promoted into an ontological discovery. Now the satisfying part, with all satisfaction kept inside the experiment that earned it. The rare environment construction contains 6 independent coordinate decisions. For each coordinate, there are 2 fragile candidates and 1 stable candidate. Fragile units perform well in the common environments, but fail in one rare environment. The stable candidate preserves the coordinate across all environments. The common environment prevalences are 0.499 and 0.499. The failure environment prevalence is 0.002. Importantly, the experiment still draws 320 samples from every environment, so the failure environment is statistically evaluated, even though the prevalence-weighted objective barely values it. Across 20 random seeds and 6 coordinate decisions per seed, there are 120 choices. Source-only selection retains the stable candidate 0 times. The prevalence-weighted mean also retains it 0 times. Minimax selection retains it 120 times out of 120. The resulting worst environment risk for Minimax is approximately 0.02249, plus or minus 0.00042 in the reported summary. For this small construction, every possible combined subset can be checked. 3 choices raised to 6 coordinates equals 729 subsets. Minimax matches the exact reference in all 20 seeds. That is unusually clean evidence for the mechanism. When a rare environment requires a stable activation basis, worst environment selection finds it while source and prevalence mean objectives do not. Robust refitting helps a fragile selection but cannot recreate the omitted basis. The result supports robust selection, not the universal superiority of every robust algorithm wearing a max symbol. The second controlled experiment begins with 100 candidates and compresses to 50. The generator plants 50 dominant families. It adds 25 positive rescaling clones, 15 nuisance near clones, 5 zero right distractors, and 5 low-energy auxiliaries. There are 70 known zero measured directions, but the intended dominant family count is 50. The raw right-aware hierarchy and Gaussian hierarchy, when paired with the same 5% energy floor, recover all 50 families out of 50. Their normalized reconstruction risk is approximately 0.005713 plus or minus 0.000112. Hierarchy without the floor is slightly worse, and simpler selectors lose families. This supports 2 ingredients together, right-aware geometry and filtering tiny energy candidates before selecting representatives, followed by a global refit. It does not uniquely establish that Gaussian probes are necessary because the raw hierarchy achieves the same family coverage and risk in this setup. If 2 methods tie after one arrives by limousine and the other by bicycle, the correct conclusion is not that the limousine invented transportation. The charts must show denominators, uncertainty notation, and whether lower or higher is better. The 120 result appears as a count, not a percentage floating without sample size. The 729 exact search appears as a reference badge. The 100 to 50 panel explicitly distinguishes candidate count, retained width, measured directions, and planted family. The accompanying online resource makes those distinctions checkable. It supplies raw results, summary tables, figure generation code, tests, pinned environment information, and checksums. Vespera recomputes aggregate tables from the archived rows and labels those values archived recomputed. A recomputation verifies arithmetic and data plumbing. It does not independently reproduce a model run whose inputs were already generated. The episode keeps paper reported, archive recomputed, and editorial inference badges separate, so a green checksum is not mistaken for an independent scientific replication. These experiments are designed to reveal failure mode. They are not ImageNet leaderboards, latency benchmarks, or evidence that real networks contain neatly labeled families waiting to be found. Controlled constructions trade realism for ground truth. That is valuable because we can know which unit families should survive. It becomes dangerous only when the clean mechanism is narrated as if reality signed the same assumptions. The controlled section therefore ends with a question, not a victory screen. When the families are no longer planted and the environments are natural text distributions, does the elaborate functional hierarchy still help? GPT-2 is about to answer with the academic equivalent of seen at 2:14 a.m. The real model diagnostic uses GPT-2, small at a pin model revision. It studies MLP layers 2, 5, and 8. Calibration and held-out environments are prose, dialogue, and code, each drawn from fixed corpus offsets. For each environment, the setup uses 256 calibration tokens and 512 held-out tokens. One MLP is compressed locally at a time. The retained width is reduced by 2550 or 60%. Combining 3 layers with 3 held-out environment splits produces 9 trials per reduction ratio. After changing the selected MLP, the evaluation measures held-out perplexity change by domain. The simple robust capacity selector produces worst domain perplexity changes of approximately 5.19, 6.19, and 6.95% as reduction becomes more aggressive. The raw hierarchy gives 5.13, 7.09, and 8.56%. The Gaussian hierarchy gives 6.54, 9.66, and 11.26%. At the mildest reduction, raw hierarchy essentially ties the robust capacity baseline on the headline worst domain number. At 50 and 60% reduction, it loses. Gaussian hierarchy loses more clearly and performs especially poorly in layer 2. Paired differences matter because each method is evaluated on matching layer and split conditions. Gaussian minus raw averages a disadvantage of 2.23 percentage points, with a reported 95% interval from minus 1.09 to 6.16. That interval crosses 0. Gaussian minus robust capacity averages 3.04 points, with an interval from 0.14 to 6.68. That interval is above 0 under the reported procedure. We should not convert those intervals into a cosmic referendum on random projection. There are only 9 paired trials per ratio setup. The intervention is local and model behavior depends on layer. The evidence says that this Gaussian hierarchy did not earn an advantage. In this diagnostic, it does not prove that every sketch, hierarchy, probe dimension, or calibration design must fail. This is the episode's reversal. The robust principle survives contact with GPT-2. Considering multiple environments and protecting worst domain behavior remains useful. The ornate Gaussian hierarchy does not. Simple, robust capacity is competitive or better, especially as compression grows aggressive. The Gaussian hierarchy arrives in a limousine with tung sahur on the aux, then loses to a baseline carrying a clipboard. Why might the hierarchy fail? Several hypotheses are plausible, but remain editorial inference. Random sketches may discard distinctions that matter in a real layer. Cosine geometry may not align with downstream perplexity. Local reconstruction may not predict how errors propagate through later residual blocks. The calibration token set may be too small. A planted family structure may not exist. Layer 2 may contain heterogeneous early features that punish coarse clustering. The correct response is not to choose the most cinematic hypothesis and label it mechanism. The paper reports the result. Future ablations must separate the explanations. Vary probe dimension, basis rank, linkage rule, energy threshold, calibration size, environment construction, and downstream objective. Compare against scalar baselines, raw hierarchy, learned projections, and unconstrained lowering. Measure whether local risk predicts held-out task damage. Parameter accounting also returns. A 60% reduction inside one selected MLP does not remove 60% of GPT-2. The reported local interventions correspond to roughly 0.95, 1.90, and 2.28% of total model parameters. No latency or energy measurements are reported. The video will not animate a laptop becoming 60% faster because the laptop has retained legal counsel. Perplexity also deserves plain language. It is derived from average negative log likelihood. Lower is better. A percentage change in perplexity is not the percentage of answers that became wrong. It summarizes how the model's probability assigned to held-out tokens changed under the local intervention. Worst domain perplexity chooses the most damaged of the named held-out environments. This is closer to downstream behavior than local operator risk, but it remains one metric over fixed corpora. It cannot certify reasoning factuality or safety behaviors that those corpora never test. Visually, methods begin on a complexity ladder. Gaussian hierarchy occupies the highest rung raw hierarchy, the middle, and robust capacity, the simplest. Then, the paired result lines appear. Complexity remains where it is. Performance does not salute it. A confidence interval crossing 0 receives a neutral marker, not a sad trombone disguised as statistical significance. Negative results are useful when the claim boundary survives them. The controlled experiments identify a real failure of average case selection. The GPT-2 diagnostic warns that identifying functional families in natural networks is harder than planting them. Robust objectives and functional geometry should therefore be evaluated as separate components. That is better science than forcing one method to be the protagonist. The protagonist is the question: which behavior did compression erase? And under which environment did we bother to look? What survives the full evidence chain first? A hidden unit is better described functionally by where it activates and what it writes than by either side alone. Second, environment-normalized risk can expose failures hidden by source-only or prevalence-weighted reconstruction. Third, robust selection and robust refitting are different interventions. Refitting can optimize surviving rights. It cannot recreate an activation basis removed during selection. Fourth, functional hierarchy can recover planted families in a controlled construction, especially with a compatible energy policy and global refit. Fifth, the same elaborate Gaussian hierarchy does not establish an advantage in the limited GPT-2 diagnostic. The robust objective transfers more convincingly than the particular clustering machinery. What does not survive is a claim. This is not a demonstrated state-of-the-art compressor. It does not establish production speed-up, lower energy, universal robustness, automatic discovery of true intrinsic width, depth compression, or safety across environments that were never represented. The article's public record includes an AI-assisted review ledger, the episode will call it that, rather than upgrading the label through enthusiastic typography. The next experiments are concrete, scale calibration sizes, repeat across model families and larger layers. Use environments defined by language, domain, task, and known safety behavior. Compare local reconstruction with end-to-end loss and behavioral evaluations. Test whether environment-aware energy floors protect rare low-energy families. Report wall clock, latency, memory, and kernel efficiency after actual shape changes. Evaluate whether a selector remains stable across seeds and corpus offsets. For deployment, the lesson is not that Minimax solves fairness by itself. Environment design is governance. Someone chooses which distributions receive rows in A sub E. Someone chooses whether max risk, severity weighting, or another policy matches the real cost. Someone decides how much distortion is acceptable. The equation makes those choices inspectable. It does not make them morally automatic. A practical compression report should publish the environment definitions. Calibration counts, selection objective, energy filter, retained width, refit regularization, random seeds, local reconstruction curves, downstream metrics, and whole system performance. It should name behaviors that were not evaluated. It should preserve the original model and subset manifest so regressions can be traced. Most importantly, it should include a rollback path. A smaller matrix is easy to celebrate. A deleted basis is much harder to negotiate with after deployment discovers why it existed. Our final diagram returns to the 6 musicians. 5 common instruments remain loud. The 6th is no longer invisible. Its contribution is traced to the rare room, its risk is normalized, and the selection objective has to acknowledge the failure. Sometimes the method keeps it, sometimes the operating budget still forces a trade-off. But the deletion can no longer masquerade as harmless, merely because the average applauded. There is a broader research habit here. Controlled experiments are most useful when they reveal a mechanism sharply enough that a real model test can disagree with part of the implementation. If every benchmark is edited into agreement, the method becomes a brand mascot instead of a hypothesis. Here, the rare environment construction validates the selection principle, the family construction validates right-aware grouping under planted structure, and GPT-2 rejects the assumption that the most elaborate grouping automatically transfers. The chain is stronger because its links have different conclusions and visible boundaries. Compression is often presented as subtraction, fewer parameters, fewer flops, less memory. Functionally, it is a transfer of error. The serious question is where that error lands, how severe it becomes, and whether the affected environment was permitted to appear in the evaluation at all. If we measure only the common room, rare behavior becomes free storage. So before deleting width, ask 3 questions. Which activation directions are unique? Which environments expose them? And can the surviving basis actually reconstruct what we are promising to preserve? The meme was stupid. The missing basis was not. The smallest model is not automatically the smartest model. Sometimes it is merely the model with the fewest remaining witnesses.